As you lie here, letting your body sink gently into the bed, the world around you begins to soften. The room is quiet, the light is dim, or perhaps completely gone. Your breathing settles into a slow, natural rhythm. It feels as if everything is still. The floor is still, the walls are still, the bed is still, and yet nothing is truly still. The earth beneath you is turning, slowly but steadily, on its axis. At the same time, the earth is moving along its wide orbit around the sun, tracing out a huge circle in space. The sun itself is drifting around the center of our galaxy, the Milky Way, pulled along with billions of other stars. And the Milky Way is not fixed either. It, too, is moving through the great, dark web of the universe, among clusters and superclusters of galaxies. All of this motion is happening at once, all of it invisible to you in this calm moment before sleep. Yet there is one thing quietly guiding every orbit, every fall, every curve. We call it gravity. Gravity keeps you gently pressed against your bed, instead of floating up toward the ceiling. Gravity holds the air close to the earth, so that you can breathe. Gravity keeps the moon circling the earth, and the earth circling the Sunday. Gravity is the quiet architect of the motions of the heavens and the weight you feel in your body. For a long time, we imagined gravity as a kind of invisible pull, a mysterious force reaching across empty space. We lived with this idea, used it, trusted it, and built our science upon it. But then one man looked at the same falling apples, the same circling planets, the same silent pull downward, and saw something different. Instead of asking only, "What does gravity do?" he asked, "What is space? What is time? And what if gravity is not really a force at all, but a sign that space and time themselves are bending and curving?" That man was Albert Einstein. Tonight, as you drift towards sleep, we will slowly travel through two different ways of seeing gravity. One is the picture of Isaac Newton, a universe of objects and forces, where gravity is an invisible attraction between masses. The other is the picture of Einstein, a universe of curved spacetime, where gravity is not a pull, but the shape of reality itself. You do not need to hold on to every detail. You do not need to follow every idea perfectly. You can let the words flow by like stars passing outside a window. Your mind can drift. You are allowed to fall asleep at any point. The story of gravity will continue without you, and when you wake up, the same laws of the universe will still be holding you gently in place. Let us begin long ago, with a man watching the sky and wondering why things fall. Imagine a quiet garden in England centuries ago. The air is cool. The trees move slightly in the breeze. Apples hang from their branches, some ripe, some still growing. In this garden, a young Isaac Newton sits and watches. He lives in a world with no airplanes, no rockets, no satellites, no images of distant galaxies. But he has something very powerful, a way of thinking about motion that is simple, clear, and deeply logical. In Newton's mind, the universe is filled with objects: stones, apples, carts, planets, and stars. Each object has a property called mass. Mass is a measure of how much stuff there is, and also of how strongly an object resists changes in its motion. Newton realizes that if an object is left alone, with no forces acting on it, it will either remain at rest or move in a straight line at constant speed. This is his law of inertia. Things only speed up, slow down, or change direction when something pushes or pulls on them. In this world of pushes and pulls, Newton gives a name to the agent that causes a change in motion. He calls it force. A force can be the push of your hand on a door. It can be the pull of a rope. It can be the drag of the air as you move through it. Or it can be something more mysterious: the invisible attraction between objects with mass. That attraction is gravity. People had always known that things fall. They knew that if you drop a stone, it falls to the ground. But Newton asks a deeper question. Why does it fall in the way that it does? Why does it always fall down toward the earth? And if the earth can pull on the stone, perhaps it can pull on other things too. Legend says that Newton saw an apple fall from a tree and began to wonder why it fell straight down rather than sideways or upward. Whether the story happened exactly like that is not important. What matters is the question that grew in his mind. If the earth can pull the apple down, could the same pull reach all the way to the moon? Newton imagines the moon circling the earth. If there were no gravity, the moon should move in a straight line and fly off into space. But the moon does not fly away. Instead, it continues to fall around the earth, always missing it, always curving, always staying in orbit. Newton's great insight is that the force that pulls the apple downward could be the same force that keeps the moon circling the earth. This invisible pull might extend across the vast emptiness of space, connecting every mass to every other mass. He works out a precise mathematical description of this idea. He proposes that any two objects with mass attract each other with a force that depends on their masses and the distance between them. The force is stronger when the objects are more massive, and weaker when they are farther apart. In fact, the strength decreases with the square of the distance. If you double the distance, the force becomes 4 times weaker. With this single equation, Newton can explain the fall of the apple and the orbit of the moon in one unified picture. He can describe the paths of planets around the Sunday. He can predict eclipses. He can account for the tides caused by the moon's pull on the oceans. The universe becomes a clockwork of predictable motion. Objects move according to clear rules. Gravity is a force. Space is an empty stage where things happen. Time is a steady, universal tick that passes the same way everywhere. It is a beautiful, powerful picture, and for centuries it seems complete. But there is a small discomfort hidden in Newton's description of gravity. It is something he himself notices and is uneasy about. In his formula, the gravitational force between two objects seems to act instantly, no matter how far apart they are. When the Earth pulls on the moon, it does so across empty space, with nothing in between. When the sun pulls on the Earth, it does so across a distance of nearly 150 million kilometers. How does this invisible influence travel? Does the Earth somehow reach out through the void and grab the moon with a force that has no physical carrier? If the sun were to vanish suddenly, would the Earth immediately feel the change in gravity, even before light from the sun has had time to reach us? Newton does not know. He does not claim to know how gravity works internally. He only knows that his law fits the observations. He describes what happens, but not why it happens that way. He is honest about this limit. His theory is an effective description, a recipe that gives the right numbers. But the deeper mechanism of gravity remains in shadow. For a long time, that is enough. The law of gravitation works so well that ships use it to navigate the oceans, astronomers use it to chart the planets, and engineers use it to design bridges and machines. Newton's gravity is the language in which the universe appears to speak. Centuries pass. Science advances. We discover electricity and magnetism. We learn about atoms and chemistry. We build better telescopes. We send instruments higher into the sky. And then, in the late 19th and early 20th century, cracks begin to appear in the classical picture. Not failures of Newton's law in everyday life, but hints that there is more going on beneath the surface. One of the people who notices these cracks and decides to follow them is a quiet young man who works in a patent office. His name is Albert Einstein. Einstein spends much of his early life not in grand laboratories, but in his mind. He likes to imagine strange situations. He asks himself questions that sound almost like daydreams. What would it be like to ride on a beam of light? What would you see if you moved very fast, close to the speed of light? How would time and space behave if you watched someone moving near that speed? These questions lead Einstein to his first big breakthrough, the theory of special relativity. In this theory, Einstein accepts something that many people find hard to imagine. He accepts that the speed of light in vacuum is the same for all observers, no matter how they are moving. If you shine a beam of light and you run after it, the light does not get slower from your point of view. If you run toward a beam of light, it does not get faster from your point of view. The speed of light is constant. For this to be true, something else must give way. It cannot be the speed of light that changes from observer to observer. Instead, it must be space and time themselves. Einstein realizes that different observers, moving at different speeds, will disagree about lengths and durations. To one observer, a moving clock will tick more slowly. To another, a moving rod will appear shortened along the direction of its motion. Time and space are no longer rigid and absolute. They are flexible, interconnected, and relative to the state of motion of the observer. Einstein brings these ideas together by merging space and time into a single, four-dimensional entity, spacetime. An event is not just something happening at a place or at a time. It is something happening at a specific place and a specific time, a point in spacetime. This is the foundation for his later work on gravity. But at first, special relativity does not include gravity. It deals mostly with straight-line motion at constant speed, in situations where gravitational effects are small or ignored. Gravity is still out there, waiting for a new look. Einstein does not ignore it. He keeps thinking. He continues to ask himself odd, simple-sounding questions. One day, he imagines a man falling from a roof. If a man were to fall freely, without resistance, what would he feel? As he plummets toward the ground, in the brief moments before anything stops him, his body and all objects around him would fall together. If he dropped a key from his hand while falling, the key would float nearby, not seeming to fall, because both he and the key would be accelerating downward at the same rate. In those brief moments, the falling man would feel weightless. He would not feel the force that usually presses his feet against the floor. He would not feel his body's weight. His stomach might feel strange, but his body would be in free fall, in a kind of temporary freedom from gravity. Einstein later calls this idea the happiest thought of my life. He realizes that free fall is special. To someone in free fall, gravity seems to disappear. Locally, in the small space around the falling person, everything behaves as if there were no gravity at all. Now, imagine a different scene. Picture a small room, a sealed box, floating far from any star or planet, in deep interstellar space. Here, there is effectively no gravity. The room and everything inside it drift calmly. If you are inside this room and you let go of a ball, it will float next to you. You, the ball, and the room all float together. You feel weightless, just like the falling man. Now imagine that the room is not floating freely, but being pulled upward with constant acceleration by a rocket. From inside, you do not see the outside world. All you know is that when you let go of the ball, it falls to the floor. You feel your feet pressed against the floor. You feel your weight. It feels exactly like standing in a room on the surface of the Earth. In one case, you are in a gravitational field, standing still on the ground. In the other, you are in deep space, but accelerating. And yet, from inside the closed room, the two situations feel the same. Einstein realizes that this is not a coincidence. He forms the equivalence principle. Locally, the effects of gravity are indistinguishable from the effects of acceleration. This principle becomes the seed from which his new theory of gravity will grow. He begins to look at gravity not as a mysterious force pulling down, but as a kind of acceleration, a consequence of space-time behaving in a particular way. He asks, what if gravity is not a force at all, but the way space-time tells objects how to move? To build this idea, he needs to understand what would happen to space-time itself in the presence of mass and energy. He begins to think not of gravity as something that lives inside space-time, but of gravity as space-time. To see how this could work, it helps to imagine a simpler example, not with four-dimensional space-time, but with two-dimensional surfaces. Think of the surface of the Earth. To someone walking on it, the Earth might feel flat in their local area. The ground beneath their feet seems level. Their village might lie in what seems like a flat plain. But if you step back and look at the Earth from space, you see that it is curved, round, a sphere in the vastness of space. On a flat sheet of paper, the shortest path between 2 points is a straight line. On the surface of a sphere, the shortest path between 2 points is still straight in a certain sense, but it appears curved when drawn on a flat map. We call these special paths geodesics. A geodesic is the path that locally feels straight, even if the larger surface is curved. Airplanes traveling long distances across the globe tend to follow paths that look curved on a flat map, but are the shortest routes on the curved surface of the Earth. Einstein takes this idea of geodesics and applies it to spacetime. He suggests that objects in free fall are simply following geodesics in a curved spacetime. Instead of being pulled by a gravitational force, they are moving along the straightest possible paths in a spacetime that itself is bent by the presence of mass and energy. To visualize this, many people use the image of a stretched rubber sheet. Imagine a large, flexible sheet pulled tight so that it is flat. If you roll a small ball across it in a straight line, it will move smoothly from one side to the other. Now place a heavy bowling ball in the center of the sheet. The sheet sags under the weight of the ball, forming a dip, a curved region. If you now roll the small ball near the heavy bowling ball, the small ball's path will curve toward the dip. If you roll it just right, it may orbit around the heavy ball for a while, looping in circles or ellipses. In this analogy, the rubber sheet is like space-time, and the heavy ball is like a massive object, such as a star or a planet. The small ball is like a smaller object, a planet or a satellite or an asteroid. The small ball is not being pulled by a mysterious, invisible string. It is simply rolling freely on a surface that is no longer flat. Its path is curved because the surface it moves on is curved. Of course, this analogy is not perfect. It uses the gravity of the Earth to make the sheet sag, and it is only a two-dimensional picture. Real space-time is four-dimensional and needs no external gravity to bend. But the idea remains. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. Einstein expresses this in a set of mathematical equations that are more complex than Newton's single law, but they contain a deeper truth. From these equations, he can derive how planets move, how light travels, how time flows in different places, and how strong gravitational fields behave. When his work is finished, Einstein has a new theory of gravity, the general theory of relativity. In Newton's world, gravity is a force acting across space. In Einstein's world, gravity is the geometry of space-time itself. The two pictures agree in many situations. For planets orbiting the Sun at moderate speeds and distances, Newton's equations give answers very close to Einstein's. In everyday life, Newton's gravity works extremely well, but in extreme situations, or when we measure very precisely, differences appear. And in those differences, Einstein's view shows its power. One of the first places where this shows up is in the orbit of Mercury, the planet closest to the Sun. Mercury moves in a path that is almost an ellipse, with the Sun near one focus. But this ellipse is not perfectly static. The point where Mercury comes closest to the Sun, called its perihelion, slowly shifts over time. The ellipse itself rotates, very slightly, over long periods. Most of this precession, this slow rotation of Mercury's orbit, can be explained by Newton's gravity, once we include the effects of other planets pulling on Mercury, but not all of it. There remains a small extra amount, a tiny discrepancy that Newton's theory cannot account for. For years, this puzzle sits in the data, unresolved. When Einstein applies his new theory to the problem, he finds that the curvature of spacetime near the Sun, with its large mass, changes Mercury's orbit just enough to match the observations. The leftover discrepancy is no longer a mystery. It is a sign that spacetime is curved in the way his equations describe. Another test comes from the behavior of light. In Newton's picture, gravity acts on masses. Light, having no mass, should not be affected directly by gravity. Some people tried to imagine that perhaps light has an effective mass, but it is not a natural fit to the theory. In Einstein's picture, light always travels along the straightest possible paths in spacetime, geodesics. If spacetime is curved, then these straightest paths will also be curved. Light, traveling near a massive object, will have its path bent, not because light has mass, but because it is moving through a region where space-time itself is curved. Einstein predicts that starlight, passing close to the edge of the Sun, should be deflected slightly. The apparent position of the star in the sky would shift by a small amount when its light passes near the Sun, compared to when the Sun is not in the way. To test this, astronomers wait for a total solar eclipse. During a total eclipse, the Moon blocks the bright disk of the Sun, allowing stars near the solar limb to be seen. In 1919, teams travel to observe such an eclipse from different locations on Earth. They take careful photographs of the sky during the eclipse and then compare the positions of the stars on these photographs to their positions when the Sun is elsewhere in the sky, far from them. The results show the shifts Einstein predicted. The starlight has indeed been bent as it passed near the Sunday. The amount of bending matches the value calculated from general relativity, not the smaller amount you would get from trying to add gravity to Newton's theory. This dramatic confirmation brings Einstein's theory into the public eye. Newspapers report that starlight has been bent, that Newton has been surpassed, that a new picture of the universe has arrived. There is another prediction of Einstein's theory, more subtle but very important. Gravity affects the flow of time. In his equations, the presence of mass and energy not only curves space, but also influences how quickly time passes. Near a massive object, time runs more slowly than it does farther away. This effect, called gravitational time dilation, is tiny for the Earth in everyday conditions. But with very precise clocks, we can measure it. Clocks on high mountains tick slightly faster than clocks at sea level. Clocks on satellites, orbiting the Earth, tick at rates that differ from clocks on the ground, because they are both farther from the Earth's mass and moving at high speeds. These differences matter. The Global Positioning System, GPS, relies on signals from satellites carrying atomic clocks. To calculate accurate positions on the Earth's surface, the system must account for the fact that time on the satellites flows at a slightly different rate than time on the ground. Without the corrections provided by Einstein's theory, the GPS system would quickly accumulate errors, and your phone would show you in the wrong place. In this way, the bending of time by gravity is not just an abstract idea. It quietly touches the technology you might use every day. As we follow the implications of Einstein's theory further, we reach more extreme and mysterious regions of the universe. Consider a very massive star, many times the mass of our Sunday. While it shines, the star balances two great effects: its own gravity pulling inward, and the pressure of the hot gases and radiation pushing outward. Eventually, the star may run out of nuclear fuel. When it does, there is nothing left to support it against its own gravity. It begins to collapse. In some cases, the collapse stops at a new, dense configuration, such as a white dwarf or a neutron star. But if the star is massive enough, the collapse continues beyond these stages. The matter becomes so concentrated that space-time in its vicinity curves extremely strongly. In Einstein's framework, there is a point beyond which, if you get too close, not even light can escape. The surface that marks this boundary is called the event horizon. Inside the event horizon of a black hole, all paths in space-time, all possible geodesics, lead deeper inward. There is no way back out. There is no trajectory that returns to the outside universe. A black hole is not a hole in space, but a region where space-time is so strongly curved that escape is no longer possible. Its interior structure remains one of the great mysteries of physics. Far from the black hole, we might see matter falling in, heating up, and emitting radiation before crossing the horizon and disappearing from view. We might see stars orbiting a dark center, their paths indicating the presence of a huge mass in a small volume. At the centers of galaxies, including our own, we infer the existence of supermassive black holes, millions or billions of times the mass of the Sun. Their gravity shapes the motions of stars in the central regions of their galaxies. Another phenomenon arises from the curvature of space-time around massive objects: gravitational lensing. If we revisit the idea of light traveling along geodesics, we can imagine a galaxy or a cluster of galaxies acting somewhat like a lens. Light from a more distant galaxy travels through the universe, passing near the foreground cluster. As it does so, the curved space-time around the cluster bends the light's path. To us, as observers, the distant galaxy may appear in multiple distorted forms, stretched into arcs or rings, or magnified in brightness. These images are called gravitational lenses, and they have been observed many times by astronomers. They provide not only beautiful, strange images of the cosmos, but also tools for measuring the distribution of mass, both visible and invisible, in the lensing objects. Yet another prediction of Einstein's theory is that changing gravitational fields can send ripples through space-time, like waves spreading across a pond. If two very massive objects, such as black holes or neutron stars, orbit each other closely and then merge, they disturb the curvature of space-time around them in a dynamic way. These disturbances propagate outward at the speed of light as gravitational waves. As a gravitational wave passes through a region, it stretches and squeezes the distances between objects in alternating directions, very slightly. The effect is incredibly small, but not zero. For decades, gravitational waves remained a theoretical prediction. Then, with the construction of very sensitive detectors using laser interferometry, scientists were able to search for these subtle signals. In 2015, the LIGO Observatory announced the first direct detection of gravitational waves. They had measured tiny changes in the lengths of long arms of their instrument, changes consistent with waves produced by the merger of two distant black holes. This detection opened a new way of observing the universe, not with light, but with the vibrations of space-time itself. It confirmed another piece of Einstein's picture. So far, the story of general relativity sounds like an unbroken chain of success. But even a great theory has its limits. Einstein's description of gravity is a classical theory. It treats space-time as a smooth, continuous fabric. There are no jumps, no grains, no fundamental quanta of space-time in his equations. Meanwhile, in the world of atoms and subatomic particles, another great framework has emerged: quantum mechanics. Quantum theory tells us that energy comes in discrete packets. Particles can behave like waves. Events are governed not by strict certainty, but by probabilities. There is a fundamental fuzziness in the behavior of the very small. When physicists try to apply the principles of quantum mechanics to the gravitational field described by general relativity, they run into problems. Calculations often produce infinities that cannot be easily removed, suggesting that something is missing or that the marriage of the two theories is incomplete. One of the most striking places where this clash appears is at singularities, places where general relativity predicts that curvature becomes infinite and the laws break down. Inside a black hole, at the center, the equations suggest that matter collapses to an infinitely dense point. At the beginning of the universe, if we trace its expansion backward in time, we run into a moment of infinite density and curvature, often associated with the term Big Bang. Physicists believe that these infinities are signs that we are pushing general relativity beyond its domain of validity. At extremely small scales and extreme energies, quantum effects of gravity should become important, and a new theory, a quantum theory of gravity, should take over. Many candidates for such a theory have been proposed, including approaches like string theory and loop quantum gravity, but none has yet been confirmed by experiment. At the same time, astronomers have discovered that most of the matter in the universe does not behave like the familiar atoms that make up stars, planets, and people. Galaxies rotate in ways that suggest there is more mass present than we can see. Light from distant objects is bent in patterns that imply extra mass. This unseen mass is called dark matter. On even larger scales, observations of distant supernovae and the cosmic microwave background indicate that the expansion of the universe is speeding up, not slowing down. This accelerating expansion is attributed to something called dark energy, a form of energy that seems to permeate space itself. Both dark matter and dark energy affect the curvature of spacetime and the behavior of gravity on large scales. Einstein's equations can accommodate them by adding certain terms, but we still do not fully understand what they are. In this sense, Einstein's vision of gravity is incomplete, not because it is wrong, but because it is part of a larger, still unfinished story. Despite these open questions, general relativity remains one of the most successful and beautiful theories in physics. It has reshaped our understanding of gravity from an invisible force acting at a distance to a manifestation of the geometry of spacetime. As you lie here now, you are living inside that geometric story. Your body is gently pressed against the bed. The pressure you feel on your back or your side is, in Newton's language, the normal force from the bed pushing up against your weight. In Einstein's language, it is the force that prevents you from following your natural path of free fall through curved spacetime toward the center of the Earth. If the bed were to vanish and the floor beneath you were to disappear, you would begin to fall. In that fall, for a brief time, you would feel weightless. Your body would no longer be supported. You would be in free motion along a geodesic in spacetime. It is standing still on the Earth's surface that is, in some sense, unnatural, because the ground is constantly pushing you away from your free-fall path. The feeling of weight is the feeling of being held off your natural course. Above you, the air sits in its own balance of forces. Near the Earth, space-time is curved, such that objects tend to move toward the Earth. The atmosphere is held close, its molecules pulled and compressed. This creates the pressure that allows you to breathe. Higher up, the air thins, and the shapes of paths in spacetime change slightly. Satellites circle in orbits, moving fast enough that their tendency to move in a straight line balances their tendency to fall inward. They trace out curved paths around the Earth, geodesics in the curved spacetime that surrounds our planet. Farther still, the Moon orbits the Earth, and the Earth orbits the Sun. The Sun, with its huge mass, curves spacetime around it strongly enough to hold planets in their familiar paths. If you could step outside the universe and look at it from some imaginary external vantage point, you might see a vast, dynamic network of curves, a tapestry of geodesics and surfaces, all shaped by the distribution of mass and energy. But you are not outside the universe. You are inside it, part of it, made of the same matter whose gravity shapes space-time. You are a small concentration of energy and mass, resting on a slightly larger concentration of mass, orbiting a star, drifting in a galaxy, floating in a cosmos whose full shape we are still trying to understand. All of this is happening while you rest here, breathing slowly, your eyes perhaps half closed or completely closed now. You are safe. You are held gently in place by the very structure of space-time around you. You are being carried along by the curves and flows that Einstein described. Newton saw gravity as a force, an invisible pull connecting masses across empty space. His picture works beautifully in many situations and remains a powerful tool, but he did not know what space and time really were or how they could participate in the drama. Einstein saw deeper, not because Newton was wrong, but because the universe allowed a more complete description. Einstein saw that space and time are not just a stage, not just a backdrop. They are active participants in the story. Mass and energy tell space-time how to curve. Space-time tells mass and energy how to move. Where Newton imagined gravity reaching out, Einstein imagined space-time bending. Where Newton was troubled by action at a distance, Einstein replaced instantaneous influences with local curvature and finite speeds. Both pictures, in their own domains, help us understand the world. But Einstein's picture changes the way we feel about our place in the universe. We are not simply objects being pulled and pushed. We are travelers moving along the lines and surfaces of a curved reality. Our paths are drawn by the unseen geometry of space-time. As you let your thoughts drift, you might imagine that you are floating in a dark, quiet space. There is no up or down. There is no floor, no ceiling, no walls. Just a gentle sense of motion, so slow you can barely feel it. Far away, a massive object bends space-time. Your path curves slightly, and you drift along a geodesic toward it, as if you were sliding down a very wide, very shallow slope that is not in space, but of space itself. Perhaps you imagine the surface of a calm, dark ocean. Large, slow swells move through the water, almost imperceptible. You float on them, rising and falling gently. In a similar way, gravitational waves pass through the universe, stretching and squeezing space-time around you by amounts so small you never notice. Your whole life, you have been living in a sea of gravity, of curved space-time. From the moment you were born, you were pressed down by the Earth's presence, held in its invisible embrace. Every step you have ever taken has been guided by the shape of space-time beneath your feet. The ground you walk on, the chair you sit in, the bed you lie upon, all push against you, preventing your freefall. They are the obstacles that stand between you and the geodesics that gravity would have you follow. When you jump, for a brief moment, you are closer to freefall. You feel lighter. You feel the temporary separation between you and the ground. For that instant, you are more in tune with the natural motion of space-time's geometry. If you imagine standing on the surface of a neutron star, where gravity is immensely stronger, time would flow differently for you. Your weight would be huge compared to what you feel on Earth. Your sense of up and down would be dominated by an overwhelming pull. If you could hover near the event horizon of a black hole, time for you would slow drastically compared to distant observers. Light from the outside universe would appear blue-shifted, and your own signals sent outward would be red-shifted and delayed. These are extreme environments, far from our everyday experience, but they follow from the same equations that describe the gentle pull you feel now, the same mathematics that tells us about starlight bending and black holes merging, also tells us about the slight slowing of time at the Earth's surface, the slight difference in clock rates between different altitudes, the necessity of correcting satellite clocks. The universe uses one underlying language to describe both the most violent events in distant galaxies and the mild, quiet gravity holding your body to the bed. As you continue to breathe, slowly and evenly, you can let the details fade into the background if you wish. You can simply keep a soft awareness that gravity is not just a force, but a way that space and time express the presence of mass and energy. Einstein saw something that Newton did not. He saw that to understand gravity, we must understand the nature of space and time themselves. He showed us that the universe is not built on a rigid grid, but on a flexible, dynamic fabric. He gave us a new way to imagine our place in the cosmos. You, resting here, are part of that fabric. Your atoms are knots in the weave. Your mass contributes, in a tiny way, to the overall curvature of spacetime. You help shape the universe, just as the universe shapes you. The bed beneath you supports you against the Earth's pull, and the Earth supports you against the Sun's pull, and the Sun is held in the galaxy's embrace. Layer upon layer of motion and curvature, all the way up and all the way down. And yet, your experience right now can be simple. You only need to feel the gentle weight of your body, the contact with the bed, the slow rise and fall of your chest. Somewhere, far away, two black holes may be spiraling toward each other, their orbits shrinking as they radiate away energy in gravitational waves. In a final, swift dance, they merge, sending a burst of space-time ripples outward in all directions. Millions or billions of years later, a faint echo of that event passes through the region where the Earth is. The distances between objects here stretch and contract by tiny amounts, far too small for you to feel. You sleep through it, unaware, held in place by the steady curvature of space-time that has been constant for ages. Above you, constellations wheel slowly in the sky, their stars bound to the galaxy's mass. Between galaxies, dark matter shapes the large-scale structure of the cosmic web. Dark energy drives the expansion of the universe, influencing the very fate of all things. All of these are parts of the great gravitational story, a story written in the language of space-time geometry. Newton began the story with forces and equations that hinted at a deeper mechanism. Einstein continued it with the idea that space-time itself can bend and curve. We do not know the final chapter. We do not know exactly how gravity behaves at the smallest scales, or how it unites fully with quantum mechanics. We do not yet fully understand dark matter and dark energy. But for now, we can rest inside the part of the story we do understand, letting it comfort rather than disturb us. Because in this story, gravity is not something hostile or threatening. It is the reason you can lie down and not drift away. It is the reason the air stays with you, the reason planets have surfaces, the reason stars can form. Gravity gathers. It pulls matter together so that clouds of gas collapse into stars. It shapes the galaxies. It allows planets to form around stars, and it holds oceans in their basins and mountains to their roots. Your body, made of elements forged in ancient stars, now rests in a gravitational field that those same stars helped shape. You are a collection of atoms, the product of gravity, chemistry, and time. You are, in a very real sense, the universe becoming aware of its own structure for a brief moment. Soon, even that awareness will soften as sleep comes. Thoughts will blur and drift. The words you hear will become less and less distinct. You may stop caring about space-time and curvature and geodesics. You may simply feel the warmth of your covers and the slow comfort of your breathing. Gravity will continue its quiet work, whether you understand it or not. It will continue to guide the Earth around the Sun, the Moon around the Earth, and your body gently toward the center of the Earth. In Newton's language, it is a universal force of attraction. In Einstein's language, it is the shape of the world itself. both languages can coexist in your mind. You can picture apples falling and planets circling. You can picture rubber sheets and curved surfaces. You can picture yourself floating in a dark sea of spacetime. However you imagine it, you are safe inside it. You are part of it. And as you gradually let go of wakefulness, you can allow yourself to fall very gently, not through space, but into rest. Gravity, what Einstein saw that Newton didn't, and what you are now feeling is nothing more than a soft weight pressing you into the bed, supporting you, grounding you, holding you. In the morning, the same laws will be there, the same curves, the same space-time, the same earth beneath you. For now, you do not have to think about them at all. You can let your mind grow quiet. You can drift. You can sleep. Dang Suinyi.